Hello, so this is going to be part one of the second day's video, just because there's more slides here than I'm able to put in the app I'm using to make videos. So today we're going to have this video, and then a few hours from now I'll post the second part to this video. So sorry for the inconvenience if you were hoping to get all of this done in the early afternoon or something like that. But yeah, so anyway, here's part one. These are the problems that, here's the first of the two problems that I assigned from the first section of yesterday's class. So there is a picture here for you. We have a grid, it's a 3x4 grid, and it's 1 unit by 1 unit blocks. So that's what the grid was supposed to look like. If you start from the bottom left and you want to traverse to the upper right corner, and of course that'll take 7 units. It'll be a 7-unit path no matter how you traverse those grid lines to get there. But the way to think about this problem, how do we find out the total amount? Well, really what a path is going to look like, it's going to be, you're going to have to move right 4 times and you're going to have to move up 3 times. So the thing is that you're going to have 7 movements total. 4 of them will be to the right and 3 of them will be up. And it doesn't matter what order you do up and to the right. So basically, you have 7 slots, and you want to place the 3 ups in 3 of those slots, and then you'll just put the rest of the right movements in whatever's left. So for example, there is an example shown right there. There's a path where you go right, up, up, right, right. That's one of the paths. And as you can see, the 3 U's were placed in the 2nd slot, the 4th slot, and the 5th slot. Now, how many ways are there to choose 3 slots to put the U's in? Well, it's just going to be 7 choose 3. And if you remember, the way that we compute that is the 3 on the bottom will tell us how many numbers we need to write on the numerator. 7 times 6 times 5. It's a descending factorial. Because if order matters, if we have three slots and we want to put numbers in there, there's 7 choices for the first one, 6 choices for the second U, and 3rd choices for the 3rd U, but then we got to divide out because order doesn't matter here, so we divide by 6 or 3 factorial. So we get 35. And that will be the answer to this first one. Now, just so you're aware, there's 2 different ways to think about to calculate the total number of ways to rearrange 4 R's and 3 U's. Now, the first way to think about it is to think about it in the above way of just doing 7 choose 3, because we need to figure out 3 locations for the U's, and then the rest of the slots we can just place the R's there. And there's only one way to place the R's there once we've placed the U's. The second way to think about this is if you think about kind of like yesterday where we had the word ball and we had L1 and L2, and there were 4 factorial ways to rearrange the letters in ball if we consider the L's as different. Well, similarly, if we consider all 4 R's as different, if we consider them R1, R2, R3, and R4, and U1, U2, and U3, well then there's 7 letters, so 7 factorial will be the total ways to arrange those letters. However, the 4 R's are indistinguishable from each other. So when we have a placement of 4 R's, there's going to be 4 factorial ways to rearrange the R's among themselves. And because of that 24:1 ratio, we need to divide by the 4 factorial there. So we start with 7 factorial, we divide by 4 factorial, because the 4 R's are all the same, and the 3 U's are all the same, right? It's not U1, U2, and U3. We need to divide by 6 because there's 6 ways to rearrange the U's if the 3 U's are in particular slots. There's 6 ways. So we got to divide by the 3 factorial, and that'll give us the same answer as if we had done 7 choose 3, which is 35. And actually notice down there how on the bottom of the page they actually have R1, R2, R3, R4, U1, U2, U3. So that's like, if you read the text in this book, you'll start to see, you'll have like a commentary about these problems. By the way, you don't need to have this book to do the class. This book is called Intermediate Counting and Probability by AOPS. So if you want to get the book, you can. And it's fine if you don't have it. You probably might have wanted to know that you could have gotten this book beforehand, but either way, I will give you 100% of the content of this book. I'll write up in notes for you, and I'll give them as handouts. So really, it's fine if you don't have the book, because I'll be giving you handouts for you to have all of the content and all of the things that you need to know just on hand. And that's why I said that you should get a folder so that you can have all of those sheets. Yeah. So don't worry if you don't have the book. It's totally fine. Also, because this is a video, feel free to just skip around if you need to. If this stuff is the basics chapter, so if this is already pretty familiar to you, don't feel like you have to watch the whole video. You can skip around if you need to. And also, if this is new to you, which it may be, just remember to sorry about that. Just remember to pay close attention to this material, and ask questions if you have them. Okay, so let's get on to the next problem that we had for homework, which is this one. So the first thing to notice, I guess it's fine if you don't notice this, but there are two ways to solve this problem. We could approach this by complementary counting, so we just forget about biter and nipper, and then we consider all the ways that we can split the 10 puppies into a group of 4 and 6, and then we subtract off the cases where biter and nipper are in the same group. So to do this, we can just do 10 choose 4. That'll tell us how many ways we can pick 4 from 10 to be in the group of 4. And then notice that gives us the total amount of ways to split it into 4 and 6. Even though we didn't compute 10 choose 6, every time we pick 4, we're leaving 6 out, and leaving 6 out is just going to be the other group. So 10 choose 4 ways, and then we'll subtract off the amount of ways that biter and nipper can be in the same group. Now, how many ways can that happen? Well, they can either be in the smaller group or the bigger group. First, let's say that biter and nipper are in the smaller group, so the group of 4. So we have this group of 4, 2 of them are biter and nipper, and now we have to figure out how many ways can we have 2 more dogs in there. So the way we do this is, well, biter and nipper are already in this group, but because there are 10 total dogs, now there's 8 dogs now to choose from to pick for those two other ones in the smaller group. So we have to do 8 choose 2. And then we have a warning here. So we're not going to do 8 choose 2 times 8 choose 6. Just like what I was saying before of when we're doing 10 choose 4, for the total amount of ways to pick dogs for the smaller group, we don't have to do anything with 10 choose 6, because once we've picked 4 dogs for the smaller group, there's automatically the other 6 are in the other group. Same thing here, because there's 8 dogs that are not biter or nipper that we need to pick from in order to put in the group of 2. We're not going to multiply that by 8 choose 6, because when we choose 2 dogs out of the 8 to complete the group of 4, the other 6 are automatically in the other group. So we're just going to compute 8 choose 2. Okay, and then case 2, if biter and nipper are in the larger group, well, the larger group was the group of 6. So in the group of 6, if biter and nipper are 2 of them, then we have 4 spots left, and we have 8 dogs to choose from for those 2 spots. For those 4 spots, sorry. So we'll just compute 8 choose 4. So then we're going to take 10 choose 4 minus the quantity 8 choose 2 plus 8 choose 4, and this gives us our complementary counting method. There's 210 ways total, and we're going to subtract off ways that biter and nipper are in the same group, so we get 112. Now, the other way to do this problem, which this is the way that I thought of first when doing this problem, is by just direct casework. So it's not too bad to just think of them as in separate groups. Okay, so there's 2 cases of possible groupings. In the first case, biter's in the smaller group and nipper is in the larger group. And again, because biter and nipper they already know which group they're going into, we have 8 dogs left to sort into the 3 slots in the smaller group and the 5 slots in the larger group. So we're going to do 8 choose 3 to figure out the total ways that who biter's friends are going to be in the smaller group, because there's 4 in the smaller group. Biter's one of them. Now we need to pick 3 more. So 8 choose 3. Okay, so 8 choose 3 ways. Now when 3 out of the 8 dogs are going into the smaller group, automatically we have the other 5 in the larger group. And then we have to do the possibility where biter is in the larger group and nipper is in the smaller group. That's also going to be 8 choose 3, so we just do 8 choose 3 plus 8 choose 3, which is 112, just like the last problem. So as you can see, there's multiple ways to do these problems often. Okay, so now we're moving into probability. So the first problem here, what's the probability that a fair 6-sided die is rolled a prime number faces up? Well, the total number of outcomes there's 6 different outcomes. And how many prime numbers could we get? Well, 2, 3, and 5. So that's 3 over 6, or 1/2. Pretty easy, pretty straightforward. The next problem here deals with the deck of cards. Now, for combinatorics and probability, you absolutely need to know what a deck of cards consists of. So there's always going to be 52 cards in a standard deck, and there's 4 suits, so there's 4 different types of cards. 2 of the suits are red, we have diamonds and hearts, and 2 of the suits are black, we have spades and clubs. And there's 13 of each suit, so there's 26 cards of each color. You need to know those facts. You also need to know that as far as the cards themselves, for each suit, there's the numbers 2 through 10, and then there's Jack, Queen, and King, and Ace. And face cards are known as Jack, Queen, and King, because if you look at the deck of cards, there's going to be a face on those cards. So there's 3 face cards in every suit, so there's 12 face cards in total in the deck. Now, you also need to know that there are 2 jokers often included in a deck of cards, but you never want to consider the jokers at all unless the problem tells you to consider them. So if they ever say standard deck of cards, just ignore the jokers. Okay, so for this problem, the cards are placed in a random order. What's the probability that the first 2 cards are both red? Well, what's the probability that the first card is red? Well, there's 52 cards, and how many of them are red? 1/2 of them are red. So it looks like I'm doing method 3 here, so let's go down to method 3. And if you look at that, the probability that we do the first card is red, it's 1/2. The probability that the second card is red, well, there's 25 red cards left after we picked the first one, and there's 51 cards total left, so we got to multiply by 25 over 51. And notice that's just taking 26 over 52 and subtracting 1 from the top and bottom, because we've already done the first red card. And so if you multiply those, we get 25 over 102. Now, method 2, let's move up to method 2. This is another method to figure out this problem. You can think about this in a combinations perspective. So if we have 52 cards and we need to select 2 of them, what's the probability that they're both red? Well, first of all, the denominator is going to be the number of possible outcomes. So we're going to have 52 choose 2 in the denominator. And if you compute that, you should get 1,326. And then you can think, well, what are all the possible ways to pick 2 cards that are red from that? Well, how many ways are there to pick 2 red cards? Well, it's 26 choose 2. Because there's 26 red cards, how many ways can we pick 2 of them? We just do 26 choose 2, and that's 325. And you can simplify 325 over 1,326 to get 25 over 102. And of course, the other one, the first method is basically equivalent to the bottom method, except it's just thinking about it just a little bit different. You can just think, well, there's 26 ways to pick the red one, to pick the first card red, and there's 25 ways to pick a red card after we've picked the first red card. And then on the bottom, there's 52 cards we could have picked from, and after we picked a card, there's 51 cards we could have picked from. So you can do that as well. So notice how there's multiple ways to solve this problem, multiple ways to think about this problem. And this is especially true in probability problems. Notice in the bottom, in the third method, we thought about, okay, what's the probability? We thought about this problem in two stages, where the first event was picking a red card, and the second event was picking another red card. And what we did was we found the probability of picking a red card first, and then we found the probability of our second card also being red, and we multiplied those probabilities together. That is how probability works. So, especially with problems like these, where you have an event or like something's happening, and then you have something happening next, you find the probability of the first one happening, and you multiply it by the probability that the second thing happens. But also notice that method 2 is kind of an interesting method as well, right? We just found out the total possible ways of picking two cards, which is 52 choose two. And then we figured out, well, how many of those, out of those 52 choose two ways, how many of those are red? Well, there's 26 choose two of them are going to be red because there's 26 red cards, and we picked two of them. And then finally, I will say that the existence of multiple methods to solve a problem like this does mean that you have to be super careful, meaning that you have to be consistent with what you're doing. So if you're considering that order matters, you have to think about order mattering throughout the entire problem. And if you're thinking about unordered things, like when you do choosing, or like 52 choose 2 is the bottom and 26 choose 2 is the top, you're not thinking about order at all. You're just thinking about picking two cards at the same time, which of course is fine. You can definitely think about picking two cards at the same time. You just got to make sure that you're consistent by doing that for the numerator and the denominator. And when you're thinking about order mattering, where you make a distinction between the first card and the second card, that's also fine. You just have to make sure you stick to that throughout the entire problem. Okay, so for this problem right here, we have our standard deck of 52 cards again. And this time we're talking about if we have a 5-card poker hand, so we just have 5 cards in our hand, it's called a full house if we have 3 cards of one rank and 2 cards of another rank. And rank is going to mean the number/letter in the top, so like what card you get, regardless of the color. And the question here, what's the probability that 5 cards randomly chosen will form a full house? Now, similarly to the last problem, you could do this a couple different ways. You could think about picking the 5 cards at different times, and the first card, obviously the first card, it doesn't matter what you pick, but the second card has to be the same rank, and the third card has to be the same rank as the first two, and then the fourth card can be a different rank, and the fifth card has to be the same as that rank. And then you also have to remember to multiply those probabilities by, it's fine if you have, ace, king, ace, king, ace instead of ace, 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 king, king. You'd have to multiply by 5 choose 2 in order to account for that. You could do it that way, but in my opinion, it's a little bit harder, and the opinion of the book apparently thinks it's a little bit harder too. The easier way to think about this problem is just thinking about, okay, so how many ways can I pick 5 cards from 52? And that's the total number of possibilities that we could have. That's the total number. It's literally the denominator of how many 5-hand pokers there are. So if we think about the numerator, then we need to figure out how many of those 52 choose 5 actually have the conditions that we want. And notice that since the bottom 52 choose 5 isn't totally unordered, we need to make sure that the numerator is totally unordered as well. And here we have this concept of constructive counting. We got to think about, well, what do we need for a full house? Well, we need a rank for the 3 cards, and we need a rank for the other 2 cards. And they have to be different ranks, of course, because we can't have 5 cards of the same rank. That's just impossible. So we know we have 2 different ranks. So how many ways can we pick the first rank for the 3 cards? Well, there's 13 different ranks because there's ace, and then there's 2 through 10. So together that's 10, and then there's 3 face cards. So 13 ways to pick the rank for the 3 cards. And then we need, because there's 4 different suits, those 3 cards that have the same rank, we're going to leave 1 suit out of that. So we need to do 4 choose 3, which is how many ways can we pick 3 suits from the 4 suits to have for the 3 cards that have that rank. And there's 4 ways we can do that. Or in other ways, there's 4 ways to leave out a suit. Okay, and then part C here says that we need a rank for the other 2 cards. We've already chosen a rank for the 3 cards, so there's 12 ways to pick the second rank. And then similarly, we need to pick 2 of the suits for that second rank to be. So there's 4 suits, 4 choose 2 is 6. So there's 6 ways to pick 2 of the suits to have that second rank card. So we just multiply those numbers together. All right, there's 13 ranks for the 3 cards. There's 4 ways to pick the 3 suits out of 4, and then times 12, how many ways we can pick the rank of the 2 cards, and then 6, which is how many ways we can pick 2 suits for those 2 cards. So altogether, that's 3,744 full houses, and so the probability is going to be that over 52 choose 5. And that's kind of a gigantic calculation, but it can be done by hand. It doesn't take too long, but you do have to be pretty good at dividing by 2 and stuff. So, okay. On to the next problem. A bag has 3 red and k white marbles, where k is an unknown positive integer. 2 of the marbles are chosen at random from the bag. Given that the probability that the 2 marbles are the same color is 1/2, find k. Okay, super interesting. First of all, notice the sentence right below it. We have to compute the probability in terms of k that the 2 marbles are the same color, and then we have to set that probability equal to 1/2. So that's what we're going to do for this problem. Just calculate it in terms of k and set it equal to 1/2. So first, we can notice that there are k plus 3 total marbles in the bag. So if we're going to pick 2 marbles without caring about order, right? So we're not thinking about picking the first marble and then the second marble. We could do that technically, but this solution method here is doing it unordered. Okay, so k plus 3 choose 2. That's the number of ways to pick 2 marbles. Okay. We can either pick 2 red marbles or 2 blue marbles. Since there's 3 red marbles, we have to do 3 choose 2 because that's the number of ways to pick 2 red marbles. If there's 3 red marbles there, we can pick the first and the second red marble, second and third, and first and third. So that's 3 choose 2. And then we have to pick 2 white marbles. Sorry, I think I said blue earlier. But we have k white marbles, and we need to pick 2 of them. That can be done in k choose 2 ways. And since, we have to add up those possibilities together. So 3 plus k choose 2 over k plus 3 choose 2, and that should equal 1/2. And so we set that equal to 1/2, but our job ultimately is to solve for k. So all we have to do is just write down those combinations in a more useful form so that we can solve. Now k choose 2 is the same thing as k times k minus 1 over 2 times 1. And k plus 3 choose 2 is k plus 3 times k plus 2 over 2. And so you really need to use your algebra skills here. Get the numerator into a single fraction and then divide the fractions. Or you could do what the book does here and multiply by 2 on the top and bottom, where you're really multiplying by 1, so you're not changing anything. And then you got to and then we cross multiply and we'll get a quadratic. So after simplifying a bit, we get a quadratic, it'll factor, and we get k equals 6 and k equals 1. Now, however, in this problem, if k is equal to 1, now if there's one white marble, it's still possible for there to be one white marble. K can equal 6 and k can equal 1, because if we pick, it just says you need to pick 2 of the same color, and if there's only one white marble, then we're just basically computing when we have 2 red marbles. We can pick 2 red marbles, but we just can't pick 2 white marbles. That just won't be part of the thing. And you can check that the problem still works if k equals 1. Except you can't compute a factorial, but if you do the problem again and just let there be 3 red marbles and 1 white marble, it's still 1/2 if you just compute 2 red marbles. Okay, so next problem we have Mary and James. They're each going to sit in a row of 7 chairs. They choose their seats at random. What's the probability that they don't sit next to each other? Now this is definitely, the best way is definitely complementary counting here. It's easier to count the ways that they can sit together than it is where they can sit apart. Because there's a lot more ways they can sit apart than they can sit together. So now let's think of this correctly. So we can think about unordered or we can think about ordered. Now, unordered is where we just have Mary and James. They're just occupying 2 seats, and we don't care which person occupies which seat. That's thinking about this in the unordered way. We could also think about this in the ordered way, where Mary sits in a seat and James sits in another seat, but that is going to be a little bit more computation heavy, unnecessarily so in my opinion. So I think the best way is definitely unordered, because we don't have to worry about who sits in what seat, because it's not really important to the problem. Well, like for example, if we needed that Mary sat to the left of James or something like that, then order would matter and we'd have to consider that, but for this problem it doesn't matter. So there's 7 choose 2 ways that Mary and James can choose the 2 chairs, and of course we don't worry about the order in which they sit. Okay, and then so there's 21 ways, so that's the denominator, and then the top is going to be, well, how many of those ways can they sit together? And if you think about it, it's just going to be 6. And we can see here that, if they sit together, maybe one of them sits in seat 1, the other one sits in seat 2, and so the person on the right can sit in either seat 2 all the way to seat 7 with the other one on the left side. So 2 through 7, 7 minus 2 plus 1, that's 6. So 6 over 21 is 2 over 7. Now remember, we're not done because that was the complement, right? That's what we don't want. So 1 minus 2/7 is 5/7. Oh, and I didn't mention this yet, but when we do complementary counting with probability, the probability of anything happening is 1. So we have to take 1 minus that. Okay, so this next problem, the Grunters play the Screamers 4 times. The Grunters are the much better team and are 75% likely to win any given game. So what's the probability that the Grunters will win all 4 games? Okay, so something really interesting here for you to look at and consider. There's a bogus solution here. So you could think about this like this. Since each game has 2 possible outcomes, there's 16 possible outcomes for the series. Only one of these outcomes is what we want, namely the Grunters winning the first one, second one, third one, fourth one. Therefore, the probability is 1 over 16. This is a bogus solution, and you can tell that because we didn't use the fact that 75% of the time the Grunters are going to win, and that's not reflected in our calculation at all. The probability is not 1 over 16 because those 16 different outcomes, they're not all equally likely. Okay, so the key fact is here that 1 over 16 would be the correct answer if it was 1/2 probability of winning, for everyone, right? The denominator, you can only do combinations for probability problems when each of those combinations is equally likely. Okay, so that's the difference here. So really how we need to think about this is just what's the probability they win the first game, 3/4, second game 3/4, third game 3/4, and fourth game 3/4. Multiply all that together and get 81 over 256. Okay, so the next problem was a marble problem. So let's go ahead and take a look at this next problem. Okay, so we have a bag with 4 red and 6 blue marbles, a marble selected and not replaced, then a second is selected. What's the probability that both are the same color? Okay, so the first thing that comes to my mind when reading this problem is probability that they both are the same color. Well, let's pick a red and it's not replaced. Okay, then just pick another red. And then let's add that probability that that happens to picking a blue and then picking a blue again. And that's the most straightforward way to do this problem. So 4 over 10 is the probability of picking a red, times 3 over 9 is the probability of picking the second red because the first red is gone. That's 2/15. And then what's the probability that the first one's blue, 6 over 10, times the probability the second one's blue, 5 over 9. Multiply those together and you get 1/3. So the probability that they're both the same color, we have to add the two cases. 2/15 plus 1/3 is 7 over 15. Okay, so then we have this next problem with point C is chosen at random atop a 5 foot by 5 foot square table. A circular disc with a radius of 1 foot is placed on the table with its center directly on point C. What's the probability that the entire disc is on top of the table? In other words, none of the disc hangs over the edge. Okay. So the correct way to think about this, we want the probability that we're able to place the circle entirely within the desk. We can think about, well, what's the area of the region where the center of the circle is allowed to go, and divided by the total area that where the center of the circle can go. So if you notice this picture here, there's an unsuccessful region and a successful region. Because the radius of the circle is 1, we need the center of the circle to be at least 1 foot away from the edge. And so that successful region is going to be 3 times 3, which is 9 over 25. And so we have this general concept here. In geometry problems or in other problems in which the possible outcomes are continuous, as opposed to discrete, meaning that they can be counted, we need to use geometry to compute the probability. So the probability of a success is going to be the probability of the size of successful outcomes region divided by the probability of the size of the possible outcomes region. And that's fairly intuitive. You may or may not want to write that down, but there it is. Okay, so here's expected value. I realized for problem 1.20 I forgot to give you the table, so I'm sorry about that. You couldn't really do the problem, but we'll cover it anyway. So expected value is interesting. Basically, we have to consider all of the possible outcomes, and we have to consider what's the weight of those possible outcomes. So if you look at the green box here, it says concept. Suppose that we have an event with a list of possible values of the outcomes. Now, if the values of the outcomes, for example, it could be money or it could be something else, it usually is money. Or it could be like a number or something. Now, those are the values x1 through xn. Now, we need to figure out what's the probability of those values happening. The probability of x1 is p1, so the expected value is just going to be the sum of, it's the sum of those possible outcomes times their probabilities. So in this first problem, we have a weighted coin that has heads and then tails. Now probability 3/4 for tails, for heads, sorry, and then probability 1/4 for tails. If you flip heads, you win $2, but if you flip tails, you lose $1. What's the expected value of a coin flip? Well, the two outcomes are winning $2 and losing $1. So positive $2, that outcome has a probability of 3/4, and the negative $1 outcome has a probability of 1/4. So it's just 3/4 times $2 plus 1/4 times negative $1, which is just $1.25. This second problem here that I forgot to give you the table for last time, you literally just you take the winnings, $10, $5, $2, $1, and $0, and you multiply them by their probabilities, and then you add all of them together, just like it says here on the page. So probability of red is 2/20, and yellow is 3/20, and so on. Add them all together, you get $2.40. And there's this concept here says one common use of the expected value in a problem like 1.20 is to determine a fair price to play the game. So the fair price to play is the expected winnings, which is $2.40. So in the long run, if I were charging people the fair price to play the game, I would expect to break even, neither making nor losing money. If I were running this game at a carnival, I could charge carnival goers $2.50 to play the game, and I would expect to make a 10-cent profit on average from each person that plays. So hopefully that makes sense. Hopefully expected value isn't just some random topic or like randomly defined. It actually can have a meaning, and it's actually useful. So let's try this next problem. Suppose I have a bag with 12 slips of paper. Some of them have a 2, and the rest have a 7. If the expected value of the number shown on a slip randomly drawn from the bag is 3.25, then how many slips have a 2? Well, we can either draw a 2 or a 7. So if we draw a 2, the probability of that we can just say is x over 12, because x we're just going to say is how many of the slips have a 2 on it. Then 12 minus x slips have a 7 on it. So the expected value is going to be x over 12 times 2 plus 12 minus x over 12 times 7, and we want that to be equal to 3.25, and so we just solve for x. And so, yep, there's a little bit of algebra in this problem, but you can eventually just solve for x. So hopefully that makes sense on how to set out that problem. The expected value is always just the different outcomes that are the values times their probabilities, and then you add them all up. And that's it. And expected value is a common topic in classrooms, so that may or may not be familiar from that. Okay, here were some additional problems that were challenge problems. Here is a quick run-through of these problems. So for this class, you're going to need to know what Pascal's triangle is, and so we're just going to quickly go over what this is. Pascal's triangle is you start with the number 1, and you keep writing the number 1 on the edges, and to write a number down on a row, you write the sum of the two numbers above it. Okay, here's the better way to think about Pascal's triangle. So the nth row is is n minus 1, choose 0 through n minus 1. So if you look at that, we have combinations everywhere. Okay, so make sure that you look at this and you see that pattern there. And problem 1.23 is to prove that n minus 1 choose r minus 1 plus n minus 1 choose r is equal to n choose r. So pretty interesting here. We can prove this in a couple ways. And if you are familiar with the way that Pascal's triangle is just combinations everywhere, then you can just kind of zoom in and you can look, well, n minus 1 choose r minus 1, that number is right next to n minus 1 choose r in Pascal's triangle. And n choose r is going to be right below it. So the way that we can, it's kind of a way to justify this equation is just to show that, well, n minus 1 choose r minus 1 and n minus 1 choose r are right above n choose r in Pascal's triangle, so therefore the sum of those two will be n choose r. Now, another way to prove this, and this is the way actually that I thought of first, is just by immediately writing down the algebraic definitions of the combinations. Now, if you remember, like if you want to do like 5 choose 3, 5 times 4 times 3 over 3 times 2 times 1, you can write down combinations that way, but there's also a factorial form. So you might want to refer to that if you don't remember how to write it down in factorial form. But you can just write down n minus 1 factorial over n minus 1 minus quantity r minus 1 factorial times over r minus 1 factorial plus the n minus 1 factorial over n minus 1 minus r factorial over r factorial. So if you didn't get that, try to pause the video now and find a common denominator for those two fractions, add them together, and simplify everything you possibly can. So pause the video now if you didn't get a chance to solve that one, and try it right now to see if you get the right answer. And then, okay, so if you do simplify everything, you should get n choose r, which is n factorial over r factorial times n minus r factorial. Yes, and then I forgot about this third way of proving this formula. This is kind of the most intuitive, probably. I remember doing this in a math class quite a while ago, but this is proof by committee forming. So if you're given a club with n members, we know that we can form an r-person committee in n choose r ways. Okay, but if we imagine that one of the club members is named Bob, Bob's on the committee, then we must choose r minus 1 remaining committee members from the n minus 1 remaining club members. So there are n minus 1 choose r minus 1 committees with Bob on them. So hopefully that makes sense. You know, we set Bob aside, so we have n minus 1 people left over. And if we want a committee with r people, but we want to include Bob, we have to do n minus 1 choose r minus 1. But if Bob's not on the committee, then we must choose all r committee members from the n minus 1 people that's not Bob. So there's n minus 1 choose r committee members with Bob not on them. So if you add those two possibilities together, that is going to equal all the ways to choose r people from n, right? Because the n minus 1 choose r minus 1, that's the number of ways to choose committees with Bob. N minus 1 choose r is the number of ways to choose an r-person committee without Bob. And that adds together to get all possible ones. And there's a name for this identity. It's called Pascal's identity. So definitely write this down in your notes if you don't have this already. It's called Pascal's identity, and we'll actually learn several more combinatorial identities in a later chapter. So that'll be super cool. So there's a few ways that we were able to prove one of the combinatorial identities last time. We can either look at Pascal's triangle, we can think about committees and just think about what it means to form a committee of our people, or we can just use algebra with the factorials. Okay, and then this problem, expand x plus y to the nth power. You should know that x plus y squared is x squared plus 2xy plus y squared. And how are we possibly going to generalize this to the nth power? Well, if you can see what's happening if we try x plus y cubed, we're going to get x cubed plus 3x squared y plus 3xy squared plus 3y squared. Sorry, not plus 3y squared, just plus regular y squared. Y cubed, sorry. Okay, so if you kind of notice the pattern where the coefficients are coming from, for x plus y quantity squared, we get x squared plus 2xy plus y squared. That's 1, 2, 1. That's the third row of Pascal's triangle. And notice the fourth row of Pascal's triangle is what you get when you get x plus y cubed. So if you remember, the fourth row of Pascal's triangle is when you get 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. So in other words, the pattern is when you do x plus y to the n, you get n choose 0, n choose 1, n choose 2, and so on. So this binomial theorem here is in green. And this is super important for this class. So make sure you take a look at this and just think about it. X plus y to the n. Remember, for every possible way to expand x plus y, no matter what n is, you start with x to the n, and then you slowly descend the exponent of x, and you slowly increase the exponent of y. such that the sum of the two exponents of x and y always equals n, and the coefficients are just n choose 0 through n choose n. So it's super symmetric here, the binomial theorem. So make sure you understand how the x powers work and the y powers and the coefficients as just combinations. And also take a quick look at the x plus y cubed up there, up above. We have x plus y times x plus y times x plus y. Really, the way to think about this, a really interesting way to think about expanding that out, is that you're picking one of the terms from the first parentheses, you're picking a term from the second parentheses, and you're picking a term from the third parentheses. And so you always are picking 3 total terms, and so at the end of the day, you're getting all possible ways to have a total exponent power of 3 if you add the exponents of the x and y. Okay, so how do we solve a problem like 1.25? What's the coefficient of the term x plus 2y squared to the 6th power with a y to the 8th in it? Now, first of all, notice that we have 2y squared, so we're going to have to take that term to the 4th power to get y to the 8th. Okay, so if we're taking the y stuff to the 4th power, we're going to have to take the x stuff to the 2nd power. And that's going to correspond to the n choose 4 term, so 6 choose 4. So we're going to end up with 6 choose 4 times x squared, and then times 2y squared to the 4th power. And so if we take 2 to the 4th power, we're going to get 16, and 6 choose 4 is the same as 6 choose 2. 6 times 5 over 2 is 15, so 15 times 16, which is 240. So the answer is just going to be 240. So there's the binomial theorem and how to use it. Now, this next problem is interesting. I like this one. If you take a look at the binomial theorem on the page before, we actually kind of are adding up. We're adding up the coefficients, n choose 0 plus n choose 1 all the way to n choose n, except each of those combinations have x to some power times y to some power. Now, what if we let x and y be 1 in the theorem? We can totally do that. We can plug in x equals 1 and y equals 1 into the binomial theorem. Because the binomial theorem is a theorem, it's true no matter what x and y and n are, assuming n is a positive integer, of course, but x and y can be anything. So we can just plug in x equals 1 and y equals 1. That makes all of the x's and y's turn into 1s. And so if you plug that in, we get 2 to the n is equal to n choose 0 plus n choose 1 all the way to n choose n. Okay, so last thing about this first part of this video, we're just going to talk about summation notation. So you've definitely have had to add up things before, where you add up a bunch of things. You've probably seen this symbol before. If you look at the very bottom, you can see we have the capital sigma, that's what that's called, the Greek letter sigma, and on the bottom it says k equals 1, and on the top it says n. Now, whenever we see that, and we have an expression which is just k is going to take on the values of 1 up through n, and you're going to add up each of those values. So k equals 1 all the way up to n. That just means you're going to plug in 1 for k, then 2 for k, and then 3 for k, all the way up until you plug in n for k, and you'll add up all those together. And that's what that symbol means. And we'll practice this symbol in the future. But so you can notice that k didn't actually appear in the problem anywhere. Well, I mean, it didn't appear in the answer. K was part of the symbol in the expression, but at the end of the day, it was just 1 plus 2 plus all the way to the n. So the variable k is sometimes called the dummy variable. But let's look at another example here. The sum from I equals 5 to 11 of I squared. This means you take the expression I squared and you sub in for I, you sub in 5 for I, then you sub in 6 for I, you sub in 7 for I, all the way up to 11, and then you just add up all those different expressions when you subbed it in. So the binomial theorem has its own sigma notation. Take a look here and try to convince yourself that that is exactly the same formula that we had on the previous page. And also notice that we have an infinite geometric series. We'll come back to this if we ever need to use it in a problem, but this is when you're adding up infinitely many terms, but the previous term times a constant is the next term, and you multiply by the same common ratio r each time. The sum of that, there's sigma notation for that, and the sum, of course, is a over 1 minus r. Okay, so that's the last of the review, chapter. Just know that this stuff was meant to be a somewhat challenging treatment of all the review of all those topics in the basics. So if it was rather easy, don't worry, because this is just the review chapter. But also, if it was kind of hard for you, don't worry, because this was really like a challenging way to review all of this material. We had some good problems in there, so don't worry. Now we're going to go into a little bit more of some precursor material before we really get into the meat of this book. And the rest of today, we're going to talk about sets and logic. It's just a very, very brief overview of the material. If you've had logic with me last summer or this summer, then you'll definitely recall a lot of this stuff. And if you haven't seen this before, then it'll be a good intro. So a set is just a collection of objects. We can have a finite set where we have a finite amount of elements in the set, and an element is just a member of the set. We can also have infinite sets. So the objects in the set are called elements or members of the set, and there's two standard ways to describe sets. We have the first, which is just listing its elements. So we can call the set capital A, the curly braces 2, 9, 22 curly braces. So this set has 3 elements, 2, 9, and 22. This is the easiest way to define a set. You just list the elements inside of curly braces, and you separate the elements by commas. And then the second way to describe a set, look at the bottom here. We have capital B is equal to the set of X, and then we have a Sheffer stroke. We just say the set of X such that X is an integer. That's how that reads. So in other words, we just have the set of all X, and then we say what X needs to be in order for it to be in the set. So this is the set of all integers, the set of X such that X is an integer. And then there's another example, the set of all X such that X is a real number and 2 is less than X is less than or equal to 3. So all real numbers in the half-open interval from 0 to 3 would be in that set. And of course, we can write down lots of different sets. The set up there, we can even write it down if we don't know what the members are of the set. The members of that set is just whatever satisfies that equation, whatever that are also real numbers. So they don't have to be numbers to be elements of a set. We can say the set of all X such that X is a state in the US. We can even have sets themselves be members of sets. We can have the set of 1 and 2 and the set of 3, something like that. It's important to know we have the empty set. There is one set that has no elements in it. That's just curly braces with nothing inside of them. For example, the set of all X such that X is a real number and X squared is less than 0. That set has no elements in it, so that's equal to the empty set. Okay, and then finally you need to know about cardinality. Or I guess not finally, but next. The cardinality of a set is just how many members are inside of it. So the cardinality of the empty set is 0. The cardinality of S up there, S is the set of X such that X is a state in the US. The cardinality of S is 50. And then we also have the notion of subset. So the subset symbol is a little C with a line under it. And it just means the set A is a subset of the set B if every element of A is also in B. So it is true that the set of 3, 8, and 11 is a subset of the set of 2, 3, 8, 10, 11, 14, and 16 because you can find 3, 8, and 11 are listed in the latter set. Now, also, we also have that the set of x such that x is an even integer is a subset of the set of x such that x is an integer, because the left set is basically all even integers, and the latter set is all integers. And every even integer is also an integer, so every element of the previous set is an element of the latter set. So A is a subset of B. We can also say that B is a superset of A, and that just means the same thing as A is a subset of B. And also we need to know about proper subsets. A proper subset is just a subset that's not equal to the other set. Okay, so that's going to be it for the material for part 1 of today. I'll post part 2 a little bit later. I'm just kind of a little bit behind on posting videos, so I'm really sorry about that. It takes a while to put these videos together, and I was a little bit busy fairly recently, but hopefully this video has been helpful. You got some good thoughts in here. Please ask questions if you have any questions tomorrow. So I will post another video in a few hours as I work on it, and I need to post another video as well. So yeah, I'll see you tomorrow. Hopefully this content makes sense, and your homework will also be in the next video that I'll post in a few hours. So okay.